All right, so let's get started. It's the second lecture, Data Science for Business, and today we're going to talk about exploratory data analysis. So it's pretty much, data science is really a hands-on discipline. And so you'll be spending most of the time actually, looking at the data, analyzing data, trying to learn from data. So it's all about data. And today we're going to talk about the ways to analyze it. All right. Okay, so what is exploratory data analysis? Well, it is actually, pretty much it is what it's called, right? It's a way to explore the data without making any preliminary, without selecting any preliminary model or having any sort of assumptions. To explore the data, to look at the data with sort of open mind and try to see what information is in there, without having any hypothesis that you would like to test, or without actually using any models, trying any models. And so the goals of this exploratory data analysis is to really try to maximize your insight into the data. So try to uncover sort of some structure if it exists in the data, see if the data is dirty, see if there is some information is missing, and maybe just perform some sort of sanity checks. Right? It sounds somewhat, formal. It is not. People can do this analysis the way they want. I strongly recommend doing a lot of the things that we're going to talk about today before you start modeling, because there is a saying of, like, in computer science, it says garbage in, garbage out, right? And so if you don't have a good feel of what your data is, most likely models will not work, right? So this is like the first thing you do when you get data sets. In fact, EDA, or exploratory data analysis, as an approach was first proposed by John Tukey, and he was a mathematician and statistician, and he even wrote a book which is called Exploratory Data Analysis. And he looked into, like, there are two things you should be doing. One is you actually look into descriptive statistics, right? So you want to understand some very, very simple things about the data, trying to, compute some very simple properties like minimum of the data, maximum, standard deviation, mean, and we're going to talk about this today. And the second is very simple visualizations. Again, this is plotting the data. And in many cases, you try to plot like the raw data, and raw data means the way you got it. And there are a bunch of different types of plots. Again, if you go into like RapidMiner, you will see like probably 20 or 30 types of plots that you could possibly do. Some of them are quite useful, and we're going to talk about them today. And so that's sort of what EDA is. EDA is really sort of unbiased approach to your first look at the data, right? Trying to just understand yourself what is in the data. Okay, so data types. There are really two data types that are out there. There is a categorical data, or in other words, labels, and quantitative data, which are just numbers, right? Now, with categorical data, there are two flavors. There are sometimes just nominal data, which is, just a label. And there are also what's called ordinal or ordered data. What I have in mind here is the following. If, for example, we take a look at this table, and this is a data set you already looked at on the previous lab session. For example, here, class category, right, this column, it actually has, it's an ordinal data, because it has, first, second, third, but there is a meaning in this first, second, and third. There is a meaning in the ordering of those labels. This is just not just, say, men and women. It's not just the types of the class, right? It is, there is a particular ordering here that is important. Now, if we look everywhere else, well, here, this is, of course, quantitative data is numbers. Now, quantitative data can be discrete or continuous numbers. it's here, it's age, though, it is written as integer, so it's discrete, but you can think about, height, which will be, say, a continuous number. So that's, no brainer. Typically, when you look at the data, and most likely, within this course, and, most likely later on, you'll be getting data as a table. Typically, table rows, that's what we call instances or examples or data points or observations or samples, right? And table columns corresponds to attributes, features, variables, properties, right? So that's a common notations. So what methods can we use? Well, if we look at the summary statistics, for example, we're going to look at the range of the data. So we want to understand, whenever you get some sort of column or, some table, you want to understand what's the smallest value and the largest value, right? Then you might want to understand the mean and the median. You want to understand how spread the data is, right? The range. And maybe you can even dig a little bit deeper and look into like how symmetric the data distribution is, right? So for example, if you have negative numbers, do you have corresponding positive numbers within the data set or not? And then you try to visualize this. Again, there are multiple ways of doing it. You can do like very simple bar plots, which just shows you the counts of the numbers. Or you can do scatter plots where you go, where you try to show the dependency of one feature from another. We can also talk about histograms and a little bit more complicated plots like what's called box plot and pairwise correlation matrices. And we're going to look into them in a minute. So first of all, for some of you this might be obvious. For others, for you this is just a reminder. Those who never seen this, well, take a look and just learn this, right? I mean, there are obvious things when you have quantitative data. You can calculate the mean or average of the data points, where you just take and add up all the values and divide by the number of those items, just simple mean. But often you also want to calculate median of the data set. And in fact, mean is kind of, everybody uses it, but in fact, median is a much, much better and much more stable metric. Now, the challenge, and I just want to remind what the median is. The median is if you take your data set, you order it, and then you actually pick up the middle numbers, the number that splits it into two parts, right? So median is actually much better describes usually data than mean, because if you think about this, if I think, I don't know, about the average salary, say in Moscow, there are a lot of people who has maybe sort of minimal wage, but at the same time will have billionaires living around here, and that number will move the average. But at the same time, if I ask sort of what salary is making, what the salary that kind of splits half of the people, well, then that's going to be median. And then there is a formal definition of median, which is really, it says if you have an odd number of numbers in your data set, this is really just whatever sits in the middle, right? If you have 5 numbers and you order them, this is going to be number 3. And if there is if it's not, and if it's an even, well, you take average in between those two numbers. So that's formal definition. Now, why it is, I want to just show you a few examples why it is important. Let's say we take those 5 numbers, 1, 2, 3, 4, 5, right? And we calculate the mean. Well, to calculate the mean, you just add 1 plus 2 plus 3 plus 4 plus 5, right? Divided by 5. Well, there you go, you got your 3. Or you can calculate the median, which is, again, just the most central number here, which is in the middle when you order them, and that's what you get: 1, 2, 3, 4, 5. It's 3. So in this case, mean and median coincide, right? And so both of them are good description. At the same time, let's say our data set consists of the numbers 1, 2, 3, 4, and 9, right? Well, mean now is going to be 4 if you add them up, right? but the median remains 3. And so that tells you that median, and I mean, mean is sensitive to outliers. So it's sensitive to the numbers that are far out. But honestly, if you again look at this data set overall, it didn't change that much. We changed just one number in the data set. And so we don't want to have a metric that is very sensitive. And that's why quite often it's better to look into, say, median prices and not mean prices, right? Because median price, it means, you know, half of the items have a price below and half of items have a price above it. Another example, also mean versus median, and I just keep showing this because it comes up very, very often. Let's say, you know, we can calculate, we can look at say, for example, the prices on the housing, and this is data of housing prices, real estate listing, and this is a histogram. It just tells you how many houses with certain amount of prices. And if you calculate mean price, it's going to be right here. So, you know, 4,500,000, right? Which tells you it's pretty expensive. But in fact, the median is right here, which means the majority of the houses actually have, you know, half of the houses have a price under or within the 200,000, and then there is, you know, some number higher. So again, median is much better representation than the mean. Now, why then typically, you know, and very often in formulas, and you'll see people using mean. Most of the time, it's just because mean is much easier to compute, right? You know, adding up number and dividing by how many there are, it's no brainer. Median, you actually have to order them, you have to rank them, and then find the center. And if you think about computational effort, you know, adding all the numbers is like n operations. And if you think about, you know, first ordering them and then taking center, it's n log n. So it's just, it's more operations. So it's just more computationally intensive. Plus, you know, you cannot put median in the formulas easily, right? So people often do mean, but typically when you deal with statistics, especially when it is like that, you know, you want to check median. Now, if you check both mean and median, if they're next to each other, most likely you have some nice symmetric Gaussian distribution. If they're far apart, you need to pay attention. Does it make sense? Okay.
Yes.
All right.
Yes.
So, guys, so this is not a rocket science. This is not algorithms and models yet, but this is something, the basics, which, you know, will help you later on analyzing the data. Now, next the histogram, right? We typically use histograms when we want to calculate, you know, how many of, you know, different, how much data lies within certain sort of bins within certain regions. Now, histograms, I'm sure you all done many, many times. There is one sort of word of warning that histograms are typically very sensitive to the number of bins. And so, yes, they show the same things, right? But depending on the number of bins, you might be able to see things or not. And if I, for example, take only a few bins, I will see what I see here, right? And this is not going to look like a distribution a lot, and that's going to be very, very sort of skewed, right? If I go here and make very small bins, I might see a very, very spiky distribution, but, you know, at least this tells me something. Probably the optimal here is in the center. So the rule of thumb, the idea would be to, you know, start with lots of bins and then see if they're too small, right? And your distribution looks very, very spiky, and then just make them a little bit wider and until you see some more or less, you know, histogram without a lot of missing points. Okay. All right. Next, you know, variance and standard deviation. You know, we typically talk about, again, people talk about mean and variance for the data sets, and that's, you know, perfect metric when you have a nice and symmetric data set. When it is not symmetric, you know, it has less importance, but it's still good to compute. So variance is defined as sum of the differences in between all points and the mean value, right? Normalized. And standard deviation is just a square root of it, right? When people talk about mean and variance, that's what they talk about. Now, Why is this important? Well, if your distribution is like this, which is more or less like Gaussian, like sort of bell-shaped, right? Typically mean will be in the center, and the standard deviation will show you, the breadth of this distribution. Now we're going to see in a one slide more precise picture if your distribution is perfectly Gaussian. On the other hand, if your distribution is like that, what we see here on the right, this is more of what's called power law distribution, and in that distribution, you have a lot of data points, so the small values, and much smaller in the large values. And so here, first of all, you instantly see that mean and median, they're not the same anymore, right? And then standard deviation, well, it really doesn't mean a lot, right? I mean, it doesn't tell you a lot. Versus here, it actually tells you that most of the data is within that standard deviation. And we're going to see in a second how much of the data it's, around 67% of the data typically if it's Gaussian distribution. So again, mean and variance are great measures if your distribution is nice, smooth, and have this bell-shaped, Gaussian shape. It's actually not that useful for other type of distributions. Now, good news that, in real life, a lot of distributions look like that. And so you're safe. Well, unless you end up having this type of distribution. And that's why this is one of the simple reasons why it is very, very important not just to blindly calculate mean and variance, but also try to actually draw the histogram and visualize the data. Because there is your eyes is the best instrument here to actually detect the behavior of the data. Okay, now we're going to talk about we're going to explore further techniques on this example. This is called Iris Dataset. It's so famous that it comes with any machine learning software, and it also built into RapidMiner, so you can easily extract it and work with it. Now the idea is there was actually, and I mean I never knew this until I of course found this data set. So that iris, there was actually 3 types of irises, right? Well, that's all I can say. And they differ by the length of and the size, the shape of the leaves, right? Some are more elongated, some are less elongated. And so for somebody who is an expert, botanical expert, he can actually, by looking at the iris, they can distinguish which type of iris it is. But for those of us who are not, in fact, the scientists, they made all the measurements. And in fact, what they measure is the size, the length, and the length and the width of this type of leaves, which is called sepal, and then this smaller one, which is called petal. And it happens then that for those 3 different type of irises, they are different, okay? And so the data set looks like this. So you have species or types of irises. There's versicolor and setosa and virginica. And then you actually have the measurements, sepal length, sepal width, petal length, petal width. Now, whenever you start working with any data, and later on, of course, we're going to be working with business data, but the first thing you do is you sit down with the owners of the data, right, with the business owners, and maybe with IT guys, whoever provides you the data, and ask what's in the columns, right? Because this is the first question for you to actually understand that. And now that's what we're doing, right? We're not just understanding that these are just numbers that are there, but we're actually trying to sort of map it onto the physical world and see what they actually mean. All right? Okay, good. So now we have the data. Let's try to explore it, right? We know that these are about flowers. We know that that's about the shape of their leaves or flowers. Let's see what we can learn from the data. So first of all, we can look at this very simple histograms. And these are three species, right? Setosa, versicolor, and virginica. And this is a sepal width. Just to remind you, this is a sepal, and we're going to be looking at this, right? Not that it is important for the algorithm, but it is just important for us to understand, what we're trying to learn here. Okay, and so this is sepal width for three different types of three different species. And we notice that, in fact, it does look quite Gaussian, right? It's a little bit shifted. If you look at this distribution, it has a maximum probably somewhere here. This is probably a little bit left compared to this. So there are some differences, right? We can actually see it from these histograms. Okay, good. So let's move on. And again, think about this. It's not like we care about irises, but we care about the approach, the methodology, and the techniques, the exploratory technique. And so that's what we're focusing on right now. Now, second thing we can do is we can actually try to build what's called scatter plots, right? And scatter plots is really putting on one axis one feature, on the other axis another feature. And so we're trying to understand the relationship. So the way it's done here is I also added colors to the plots. And so what we see here is a sepal length and sepal width, right? So and then petal length and versus petal width. Again, to remind you, we're looking at these measures, that's on one plot, and then this measures on another plot, right? So in some sense, it kind of will tell us about the shape. And what we're noticing, and I also color-coded this based on the type of the species. And so we notice that there is, group of points here, and then there is, green and those brownish points overlap. So every point is one sample, one measurement, one flower that has been collected and recorded, right? And so there are a few things you can notice, actually. You can notice that this guy is kind of, separate from the rest, which means, for certain sepal lengths, there is certain sepal width. For this type, for setosa, that is different from others. And so, in fact, it means that we could possibly, using some automatic algorithm, can detect those groups of points. And in fact, we're going to learn this class. It's called clustering. We're going to learn it in a couple lectures how to do it. But right now, we're just visualizing. By looking at this, I'm seeing this, I'm like, okay, well, there's probably a way to, split this and differentiate, distinguishing between sepal and, between the blue dots, which is setosa, and these guys. I can also plot petal width, and interestingly enough, there is also, these guys are in one corner, then these guys are all together. But in both cases, we see a very, very clear direction here, the trend, which really tells you, and it makes sense to have this diagonal trend, because what it says is the larger the petal, the petal length, largest petal width, right? So in some sense, the leaf growth proportionally, right? The larger one side, the larger another one. Here you also observe that, but it's less pronounced. Here it is very, very pronounced. Okay. You could probably extract some more sort of insights from this, but that's what I would, that's what I see here. Okay. Now you can actually combine those two plots, and you can put this, for example, here I put petal length versus sepal width, and I also put histograms on top. Notice that I also introduced the smooth version of the histogram, which is the distribution density. And that's sometimes even more helpful to have, because it kind of takes care of that binning problem, right? Where you don't know how many bins to introduce. You can actually make an algorithm to compute this very smooth curve for you that represents a histogram, right? It will not have the small thing, but it will go for, it might, kind of cover those empty spots and smooth out the top size. Now, you can actually combine all of this together you can combine all this together and have this scatter matrix, right? What we see here is we're calculating all of them, all the width. I mean, we're plotting all the parameters against each other, right? So this is actually probably the most useful plot I would normally do when I explore the data. I would actually start with this type of scatter plot because I really don't know if I have like 10 columns, which pair to calculate. I would rather just go through all of them, right, in one shot, and see which are informative and which are not. And for example, here on the diagonal, we'll have the histograms, right? Those that we did before. And those histograms, they correspond, of course, like this is for 3 classes of sepal width. This is for petal length. And here we have all possible pairwise comparison. All right. So this is one of the, quick ways to have a good look at the data. Now, honestly, I should tell, it probably works up to when you have like up to 30 features, right? After that, this matrix becomes kind of too large and unmanageable. But, I definitely, whenever you have it, I mean, you can probably pick up, if you have a larger number of columns or larger number of features, pick up some of them and then build this type of matrix. Again, this is probably one of the most useful tools you can have. Any questions so far? All right, moving along. Now, here is something that is not obvious. All the previous data, and the visualization were quite obvious, right? We just put a point with 2 coordinates. Each coordinates correspond to the values. Here we have this weird box plots. Now, how many of you know what box plot mean? Okay, I see one hand.
I do.
Okay, I have 3 more hands. Excellent. Well, and I have somebody even typing in. All right, let me explain a little bit, and then we'll come back and talk about this. But I want you to notice that it actually consists of, first of all, a box, right? And then there is a line in the middle. And for those of you who don't know what this is really, not just a bar there. It has a meaning. And then we have, it's actually called sometimes box and whiskers plot. We have those 2 whiskers, and then we also have sometimes some strange points outside. So let's quickly look at what this is. And in fact, it's the same John Tukey who introduced explorative data analysis. He also introduced this idea of box plots as this 5-point summary of the data set. So the idea is the following, that you take all your data and you split it, you order it, right? And then you split it into 4 equal parts in the numbers of data points, right? So you're going to have 1 quarter of your data set, then another quarter, then another quarter, then another quarter. All right. So you just, you order your data and then split it into 25% of the data, 25, 25, 25. All right. So that means instantly that this, if you think about this as being the 50% of the data, and that's another 50% of the data, that's your definition of median, right? And that's the line that you see usually in the middle of this box plot. This is the median of the data set. Then the other 2 lines is to the left and to the right. This is 25% of the data that is above median and 25% of the data that is below median. Actually above median and below median. And so this box plot is 50% of your data. So half of your data is there. All right. Then what you do is you take this half of the data and it's called IQR, which is interquartile range, right? Which is the size of 50% of the data. Then you go to the left and to the right by 150, right, by 1.5. And then you expect all the data to actually live in there. So whatever left out, what's sort of further out, those are outliers. And so in fact, you can kind of represent all your distribution with this with a data minimum, with those 4 quartiles, and with the data maximum. Okay. So now let's go back to this slide, and we understand now what it means. It means if I look, for example, these 3 classes, Sitosa, versicolor, and Virginica, and I look at sepal width, we understand that 50% of the samples have sepal widths from here to there, right? This is 50% of Sitosa, 50% of versicolor has it here, 50% there. And then these are the quantiles, so we can also see that how things are shifted. And these guys, what this means, and there are some samples there that look strange, right? Because majority of the data, 50% of the data here, these are just too far out. And most, it's very possible, okay, it could be a weird flower, right? Something went wrong with it, or it could be a, error in the measurement. So, when later on, when you start, for example, doing more of processing of the data, we might actually try to ignore those points, right? Remove them from data set because they're just too far out, okay? And here I did the same type of study for the, I just, instead of looking at 3 different types of the flowers, I looked in particular, sepal length, the way it, how it's distributed, width, petal length, petal width. So for me, when I try to understand this, I think always about like, I can draw a histogram along this, right? And this is sort of the representation of this histogram. That's what it is, right? Sort of summary. Now, again, the first time you see them, if you've never seen this before, they look strange, but when you get used to them, they're quite useful. And they're actually quite popular, those type of box plots. One last thing, that if your data is Gaussian, and again, we have a lot of data that distributed, almost like Gaussian, then this, first quantile, right, 50% of the data, it's right here. It's a little bit less than 1 sigma. 1 sigma gives us 67% of the data for Gaussian. This is 50%, but that's sort of what it looks like. Now, does this make sense? For those of you guys who have never seen this box plots before, does this make sense? All right. Yes. Okay. Let me know if it doesn't, right? Okay, moving along. So the next metric that we want to use when we look into analyzing data is correlations. So we want to understand if one feature is increasing, right, what happens to another one. So we saw, for example, for petals, if petal length is increasing, petal width is also increasing. And there's a metric that allows us to detect that. And that metric allows us to, there is a numerical sort of way to compute it. And that's called Pearson correlation coefficient. In fact, there are multiple ways to compute correlations, and there are multiple types of correlation coefficient. Pearson correlation is the most popular. That's the way it is computed. Again, what's done is you calculate mean of distribution and a gain mean. You take the data points, you see how far they are from the mean for one axis, for another axis, multiply, sum, all right? And then you normalize it. So this Pearson correlation has this nice property that, for example, when data is kind of nicely randomly scattered, it is equal to 0, right? When it kind of nicely aligned along the diagonal, the correlation coefficient will be 1. When it is nicely aligned along the other diagonal, it's -1, right? So what does it mean? It means we're increasing to the right, it's decreasing on, so increase in one variable corresponds to decrease in another. Here increases one variable corresponds to increase in another. And then everything in between, right? So if it is close to diagonal, correlation coefficient will be large. Then it's getting kind of smaller, and then it is 0 when it's completely scattered. again, this is like insanely helpful tool, you know, calculating correlations in between your features. And it can be even, it will be even more important later on when we start building algorithms, because, you know, it feels like the more features, the better. But sometimes for some type of algorithms, those features that are correlated, those that behave the same, they actually make algorithm perform worse, right? So algorithm getting confused by the features that change the same way, that affect the result the same way. So it's very, and it's one thing. On the other hand, on the other hand, you don't want to carry along, you know, the features that are repetitive. And so this is also a way to kind of get rid of extra data. And especially if, for example, you're actually planning an experiment and this is data that's being collected, you also making like less work for people who are collecting data. So here's an example for the iris data set. I took that data and I calculated, you know, correlation matrix for it. And I plotted it on the right. And you notice, you know, color coded it from 1 to -1. And so you notice, for example, that, you know, petal length is highly correlated with petal width. So coefficient 0.96, which means, you know, this one increasing, that one increasing. But for example, you know, petal length is anti-correlated with the sepal width. All right. So
you turn off your microphone.
Все равно не слышно.
Sorry, guys. Yes. Can you hear me now?
Да.
Okay.
Да, можно слышать.
Okay. All right. So that's sort of what you get here, and this is also quite, you know, quite valuable tool. Now, I think one of the points I want to make here with this is that we always, you know, trying to come up with different type of visualizations, but in fact, there is just a few of those that are helpful, right? And these are quite helpful visualizations. So, you know, try to kind of learn from these slides, you know, the way we visualize the data, all right? Okay, next one. Next step is going a little bit further. Now we try to actually learn something more about the data. And if you look at this, for example, data points, in fact, this is how sales relates to TV advertising, right? This is real data of how sales of particular good related to TV advertising, right? To the spend on TV advertising. And of course, there is a relation, right? The more you advertise, the more, you know, people buy. But there is a sort of quite a lot of spread here. Now, at the same time, we do see that there is a trend here, right? There is a sort of dependency, there is a trend. And so we can, you know, sort of think about this. Okay, maybe not like that. Okay. Let me try to draw it, you know, maybe like that, sort of, right? You know, we can think, we want to detect this linear trend. And there is actually a way to do this. It is called linear regression. And so what we're really going to do is linear regression tries sort of multiple lines, right? And calculates the one that describes your data points the best way. Now, what does it mean, describes it in the best way? Well, let's take a look. So what we're trying to do here is we're going to try to calculate the distances from the data point to the line, right? And for all the data points that we have, we want to calculate those distances, right? You project it onto the line and you compute that distance. Then you add all of them up, right? You add all those distances. And what do you do after that? You have this line, and it's clear that if you position it differently, that some of the distances will be different, right? You know, if I, for example, draw the same line, sorry guys, I have delivery, and they of course couldn't deliver it some other time, right? Just give me 1 second and take a look at this. Sorry. All right, this strange world. You know, you could look at the different lines, and the idea is that we try to calculate the distance to those lines, and we select the line that has the smallest distance, the smallest total distance from every data point to that line. All right, and that's pretty much the principle of linear regression. Does it make sense? Okay. You can nod your heads, right? And so then the idea is that we represent the data points, we represent you know, all the data points with this curve, which is, okay, sales is a function of total advertising volume, right? And then there is 2 coefficients, and it's a line, y equal ax plus b. And pretty much what algorithm does is it just finds those coefficients a and b, and then you got your line. All right. So we can actually use this on our iris data set. Let me clear all the drawings. We can use this on the iris data set, and then you're going to see it that for different types, you have. For different species, you have slightly different angles, right? So this is going to be described by this line, and this is going to be described by those lines. All right. Now, what you see here is actually a spread or the confidence interval. We're going to talk about them more when we talk on the lecture about regression. So when they come from. But for right now, I just wanted to tell you that one of the sort of simplest and easiest possible things for you when you explore the data, if you want to detect trends, is to just run linear regression. Always works. Might not make sense if the data doesn't lie along the line. But it's easy to do, and it doesn't hurt to try. All right. And if it works, there are metrics that tells you how well it works. Now, finally, one more class of data that I want to talk about today is what's called time-dependent data. Now, time-dependent data is, it's quite special data. It has this parameter time, right, which is different from everything else, and it sort of goes only one way. And this is the way you usually handle it, right? There are certain type of operations you can do with time data, right? And one of them is selecting window, and another is performing operations within that window. Now, this is actually simulated data. Sorry guys, this is getting insane. I'll have to interrupt for one more second. All right, so there is this window, right? And for example, one of the operations we might want to do within this window is to do what's called mean filtering. So this is different from the reason I'm kind of talking about these operations now when I talk about time-dependent data, because it is quite different. You don't usually do this in other types of data sets. Now, so what we're going to do here, we can actually take a window, and then for every data point within the window, the data point at the center of the window, replace it by the mean or average or median of the data points within that window. Now here I exaggerated. I showed a big window. In fact, it's it's much narrow window. It can be like only a few data points. And then what you do is you take this window and you slide through a data set. All right. So you're sliding this window, and within this window, you replace the values in the data set by the average within that window. And it's called sliding window. And it's also called filtering of the data. And for example, you can have what's called mean filter. And the result here is that instead of this data that is that oscillates a lot, and actually if you look at the left, it looks a lot like a stock market. It's not the stock market. This is randomly generated data, but it actually tells you that the stock market is pretty damn random. So this is the simulated data. This is a filtered version, and you see much smoother versions of the data. Now, you put very large window, you smooth it a lot, you lose the features. You put very narrow window, it has very, it oscillates a lot. So for you as a designer of this filter, it's up to you to select the right range, the right width of the window. We're going to talk about, we'll have one lecture dedicated to the time-dependent data later in the course. Now, speaking of time-dependent data, right? And I told you that we're going to actually look into those things, and it's maybe not a happy example, but it is sort of example that's I think valuable for all of us. And we'll also give you some data to try, for the homework. Now, this is as of yesterday, right? This is COVID-19. This is what we see. Now, this is across entire Russia, not only Moscow. Date, total number of cases reported. If you notice, well, as mathematicians, this is a beautiful growth, right? It's very nice, very consistent. Now, it's actually scary as shit, but it's growing very fast, and it's growing constantly, and it's 5K, 10K, 15K, etc. Now, what's even more interesting, if you calculate the daily cases, and to do this, you do like, simple differencing, right? The number of reported cases today minus the number of reported cases yesterday, right? That's the difference. What you see on the left, in fact, it's surprisingly growing the same way, right? Very, very similar way. Now, there are a few points here and there, but we know that, the way things are being reported, of course, it's not very, there might be some mistakes here and there, and then it's also a statistical process. But still, it goes pretty much very, very similar to the picture on the left, right? So let's try to do very simple modeling. Again, we're going to do right now a very naive modeling, but it gives you an idea of the sort of power of even very simple modeling and analysis of this. Again, we see this, we see that. Let's look at, now, when you see that type of growth, very fast growth, right? You think exponents. So the idea is that if you have data that's growing exponentially fast, then you want to look at that data in a different coordinate system. Instead of having here, plotting here number of cases, you would want to plot logarithm. And we'll see in a minute why. Okay, so what I did here is instead of those bars, right, I just plotted the tops of the bars. And you will see to your huge amazement that it fits on a very, very nice smooth curve. I haven't done any post-processing, any smoothing. This is the way it's actually growing right now. And then if instead of just number of cases, I plot logarithm, you'll see a straight line, right? which is, I mean, you know, again, from the scientific point of view, this is, you know, incredible that simple mathematical formulas actually work so well. And we're going to see the formula in a second. We're just going to build it, right? It's sort of so trivial that it surprises. It's scary how simple it is. But anyway, this is what you see. Take logarithm, and all of a sudden you see a straight line, right? Which tells you the date and tells you, you know, how many cases, logarithm, and then you can convert back to the total number of cases. Now, the point of doing this is very simple. You want to understand what's going to happen in 3 days, right? It is very hard to imagine with this curve because with that curve, you kind of, yes, you sort of see it somewhat, right? It's probably might go, maybe goes there, or you know, maybe it's kind of going to be, I mean, who knows, right? With this one, it's kind of obvious, right, what's going to be happening. Unless there are some drastic measures taken, right? This line will remain line. And then you can calculate what it's going to be looking, what it's going to look like there, right? So what you can do is you extrapolate on this, on the straight line, because it's a straight line. It's very easy. And then you can recalculate, recompute it there. Now, having said that, of course, you know, the measures that are being taken and all the quarantines should actually change the slope of this line, right? Hopefully. But we're not seeing it yet in Russia. It has happened in other countries. We're not seeing it in Russia. And you see, this is the real data. In fact, for the homework, we'll give you the data set that has pretty much, you know, the rest of the world. And so you'll be able to compare and see the growth rates in different countries. Okay, so what's the model? Well, I mean, it's really, you know, embarrassingly simple model. It's now in no way, it's a real epidemiological model. There are models that, you know, do much better job in prediction, but in this exponential growth phase, it just works, and it works easily, right? So let's just go over it so you would understand, you know, where things coming from. You know, the main assumption is that the number of cases the next day is equal to the number of cases today times some coefficient, some number, okay? Now, in real life, this number, this R of t, is actually changing and hopefully decreasing, right? And pretty much all the processes, all the quarantines should actually lead this R to decrease. But for a second, let's imagine that it stays the same, that it doesn't change, all right? Again, we're building a very simple model. Let's say tomorrow is today's, the number of people that are infected tomorrow is the number of people infected today times, I don't know, 1.5, all right? Wow, that's too large, okay, like a 1.3, which is a 30% increase, right? 100 people today, 130 people tomorrow, right? Then times 1.3 for the next day, et cetera, et cetera. Okay, so if that's the model, then it's very easy. So number of people day one is, you know, number of people on the day 0 times this number of people of day 2, this number times number of people on the first day, which is R squared. And, you know, just keep doing it. You realize that on the time, on the day of the time t, it's this coefficient to the power t, right? And that's the scary part, that it's just, you take this coefficient and you put it into the power. And that's what growth fast. Now, if you actually keep doing this type of exercise and look at the daily changes, and I call it daily change, which is daily NT, which is this NT plus 1 minus NT. And then you just plug in this original definition, you will surprisingly see that in fact, the change in the daily number of new, or the change in the daily number of new infections is actually connected to the previous change by the same factor. So if the factor is 1.3, and today there were, you know, what, 1,000 new cases. Tomorrow it's going to be 1,300. And the day after tomorrow is going to be 1,300 times 1.3, right? And the day after, more and more and more. And it's going to be growing until we reach the plateau, right? And this model doesn't show it, but it explains what's happening right now. Now, if now we understand that the model, again, the simplest, easiest, trivial model gives us this function, then how can we find this R? How can we find this coefficient, the doubling coefficient, right? Well, easily, right? If I take this model and calculate logarithm from left-hand side and right-hand side, that's what I get. And logarithm of the product is equal to the sum of logarithms. And logarithm of r to the power t is t times logarithm of r. So if you look at this, you realize that this is again our typical, linear function. It's a straight line with corresponding coefficients. And if you can calculate this linear regression on this line, you can calculate, you find the coefficient of linear regression, you can easily calculate R, right? So that's very simple. Okay, well, and there you go. This is our data. This is Moscow. Now, the way I calculate it, I put here days since 100 confirmed cases. This is right now what people do, because you want to kind of align with different countries, and the way since the infection started at different times in the different countries, you align on some point, right? And the point of alignment right now is, among countries, you set up a day when there was at least 100 cases reported. And that's other data points, and this is a straight line. This is linear regression, the same regression as we discussed before, that actually fits the data, right? And so based on linear regression, you can actually easily calculate the coefficients. And right now, what we see right now for this average since infection started in Moscow, it is R is 1.20, which means daily growth of 20% on average. All right. Now, all the news are not all bad. There is some good news, better news. And the better news are here. If you notice, compared to, this average thing, let me clear. This compared to what was compared to this part here, we are below straight line, right? Which means that our model, and our model is this insane quick growth every day by 20%, we are overestimating, or in other words, infection is slowing down, right? Slowing down a little bit. So this 20% is what we have over, last 30 days, right? 35 days. Now it's a little slower. So if you actually try to match, and you can also do it yourself easily, you can, for example, say, okay, look, I will draw a line. Let me try to do it here. I want to draw a line, say, right here, right, through the last few days. You notice that the slope of the line is less, which means this R within the last week is less, right? So in fact, I think for today or yesterday, it's 1.17, right? So it is either 16 or 17% growth a day versus 20, which is good news because eventually we want to get to 0 growth a day. So, 17 is better than 20. Then the question would be how quickly it will be slowing down, right? Looking at other countries, we still hasn't reached the peak, which means peak will probably, you can play more with this type of model. The peak will be probably in a couple of weeks, which means it's not going to go to, 0 until probably end of May. Anyway, this is how you can actually work with data, and you have all the tools to actually do this type of very simple analysis. Any questions here? All right, look, I don't want to end up lecture in this sort of, in this mood. Let's do something interesting. Now,
Excuse me, we have some question in the chat.
Yes, sure. Oh, in the chat? Oh, there was like 17. Oh. Does the data seem cause has last night because it was plus 4,000? Yeah, there is. Okay. Yeah, it doesn't have last night. I'm actually taking data from Johns Hopkins University, and they have a 1-day delay. So, but yeah, it's very possible that in a minute. I mean, we're going to see a lot of things. We're going to see the result of yesterday's subway problem. You know, it's all affects the way R changes. But all right, guys. Sorry, there's like a bunch of comments here. Yes.
May I also have a question? Here, it was quite easy for us to normalize the process because we saw that the initial process was looking like exponential growth. However, sometimes the graph might be not so, I would say, obvious.
Yeah.
So it's going to be harder to normalize. Are there any like methods other than just trying different functions to understand which one fits the most?
You know, honestly, you know, again, in life, most of the processes, they either going to be like sort of, you know, those linear, they can be Gaussian, or they can be exponential, right? And so typically what you do, you try, you know, logarithm. You can try logarithm on both axes. Sometimes you try square roots, right?
So it's just like trying different functions with your hands. No, I see. Okay, thank you.
There is no big science in there, and in fact, this is part of this sort of exploratory data analysis, right? We're going to sort of try a few things, see what sticks, right?
Okay.
But again, when you see, I mean, logarithm is the most powerful because when you don't, you know, you try to plot something and you don't see anything in the sense that, you know, you have like some very, very sharp rays, and or when you look at the data and you see the data of very different scales, like for example, you know, tens and then millions, right? You cannot draw it on the same scale. But if you take logarithms, it's going to be 6 and 1, right? Logarithm of a million is 6, and logarithm of 10 is 1, right? So it's if you see some very, very huge variations on one of the axes, logarithm is the best. So I mean, I typically look at the data and I look at the log of the data. You know, one of those will look quite smooth, and that's what we see here again. Now, honestly, again, guys, most of the data you will not see such a, you know, easy straight line. Again, this is like sort of textbook case of exponential growth. Oh, and by the way, if it is 1.7% or 17% or 10% or 5% or 20%, it's still exponential growth, which means even with 5%, if you leave it unattended for a long time, it will still grow to millions, right? So that is a scary part of exponential growth. If you're interested, I mean, I think I have online a couple lectures that I was teaching for a different class that goes into the details of the of epidemic modeling, right? So how you actually build those type of models and sort of, you know, how you predict epidemics.
And could you please share the link or something?
Yes,
to
yes.
See this. It would
yep.
be amazing. Thank you.
Yep, I'll put it online. Though honestly, I mean, and I taught this lectures a couple of weeks ago, but I had been teaching those lectures for the last, you know, 10 years. And when we're talking about epidemics in those lectures, it was more of like sort of abstract kind of something that happened, you know, century ago last time. And yeah, it was hard to imagine. Well, anyway, so let's cheer up a little bit. Here is, you know, here's a famous actually data set. It's so famous, it has a name attached to it. It's Sir Francis Anscombe, who was a British statistician. He came up with this data set. Now, let's spend a few minutes just like sort of eyeballing this data set, right? There is actually 4 data sets here, right, combined together. And it was designed in a very special way, right? If you look at those data sets, notice, just look at them, right? So x's are all the same, right? So it's all the same x values. All the same x values, except for this one, right? Here it's all the same. And the y values are slightly different, right? In between columns. Now, the way it was designed intentionally, right? This is no accident. That the sum of all values the same, the average the same, right? The standard deviation is the same, and in fact, if we ran, and I didn't put it here, but if we ran linear regression on all those, the slope of the curve of the straight line would be exactly the same. So what would you expect from those data points, right? Of those 4 data sets? By looking just at those numbers that we, so far described as the best descriptor of, of the data. We'll think that they're what?
That they will be quite the same.
Yeah,
Yeah,
we're going to expect that they're going to be quite the same. But again, remember that this was designed specifically, right? So there's a catch, of course, here. And here's a catch. So these are those 4 data sets. Yeah. So that is the answer why you need to plot your data. Simply because, unfortunately, those 4, even the best statistics we have, they cannot guarantee you that all the data will be the same. Now, having said that, again, this is intentionally designed that way, right? You most likely will not meet this in real world, the situation when all those features are the same, all the metrics are the same, but the data sets are quite different. But it is possible, right? So there is no guarantee, so you can map it. I mean, come on, this mathematician, statistician just sort of playing around and, trying to argue that no, those 5 metrics are not enough, right? I can give you examples where things are different. And but this is sort of very famous example. Keep it in mind, and you can bring it up to anybody who would say that, like, look, I don't care, I don't need visual, I don't want to visualize the data, right? So the rule number 1, you always visualize the data. Rule number 2, you calculate those statistics, see how they're different. Okay? All right. And I think, yes, and I think this is it for today. Any questions?
There, did you plot your graphs, all of them, in this program?
Oh, this one? Oh, yeah. I actually, well, yeah, I use myself Python. The reason is because, I'm just using Python for a long time, so I'm familiar with it. And as I said, with RapidMiner, there's a steep learning curve to learn how to do things. For me, Python, I just, have those curves. I know how to do them, right? For you guys, if you, and this is done in Seaborn in Python. In Python, there is a library Seaborn that allows you to do those nice visualization. Yeah, most of this is done in Seaborn. For you guys, those of you who are fluent in Python, feel free to use Python for the homeworks, absolutely. But I don't want to make it required for the class, simply because we have a lot of people who who are not programmers, right? And so I don't want to mix programming and actually learning algorithms. But the other thing, I have a lot of colleagues at at work who are incredibly efficient with Tableau and with Alteryx, which Alteryx is similar to RapidMiner environment. And they, in fact, can analyze data much faster than me, right? So programming language gives you extra flexibility if you want to do things, but it actually more effort and takes more time compared to all the tools if you learn them, right? So I think even for those of you who are Python programmers, still spend some time learning rapid minor, it might be useful for you in the future.
Could you share your code, if it is possible, your
Sure.
Python code?
Yeah, absolutely. All right, okay, guys. So we're gonna have a seminar. It's gonna be also on the different, on the different Zoom number than it was last time, right? And it is in the Telegram, in the Telegram chat. And the reason, again, we're switching to, HSC setup. All right, okay. And I'll, have a good, safe week. Stay safe, stay home, and I'll see you in a week.
Thank you.
Thank you very much.
Thank you for lecture.
Bye.
Thank you.
Bye.
Thank you.
Thank you.
Bye.
Bye.
Bye.